flows. I request Professor Stepanyants, please start.
Hello, everyone. I will present this talk, which was prepared in collaboration with my colleague, Alexey Slunyaev. Actually, it was a development of our previous presentation, which we made about a year ago. And since that time, we had some progress, and I will present today the results obtained. First of all, I'll remind you about the motivation of this study, but in such audience, it's apparently unnecessary. Anyway, very large area of Earth's surface, as you know, is covered by ice, and okay, and there are. I'm sorry. There is a postman. Just a moment, I will come back. I'm very sorry. Okay, I will continue. So we have also in polar regions, so-called marginal ice zone, which is covered by broken ice and by floes. The properties of the floes can be very different. They depend on thickness, size of the floes, and density of floes distribution on the ocean area. There are also artificial device covered on surface, place on the surface of the seas, and they can be considered as artificial floes. So wave propagation through such areas is very different from the wave propagation in the free surface, and the decay rate is also different from the decay rate on a free surface. As well known, when we consider water waves in viscous water, the decay rate can be evaluated analytically and is presented in particular in these classical books. So the wave amplitude decays exponentially with time, with the characteristic decay rate, which is proportional to squared wave number, k squared. This can be recalculated in terms of the spatial wave decay. In this case, the decay rate is proportional to frequency to the power 5. So this is the result of analytical study. But for water surface covered by ice, the decay rate is different, and the dependence on frequency is also very different. And as well known, such results were presented in the review by Malin and co-authors. And as you can see here, the observational data show that the decay rate can be fairly different, where the power omega to n can vary from 1.9 to 3.6. Apparently, such big divergences can be explained by different properties of flows. As I mentioned, apparently they depend on the flow size, flow thickness, and flow distribution on the ocean surface. We will consider some average value for this parameter n in our study, and we will choose n equals 3. Then we will consider wave trains which can be described by this equation, where omega naught and k, omega naught is a frequency of a carrier wave and k is a wave number of a carrier wave, whereas function sech describes the envelope of the wave train, where T capital is the characteristic duration of the wave train. So we can see that the shape of wave train depends on this parameter T. If this parameter T is big enough, we have quasi-monochromatic wave. When this parameter is relatively small, we have such a relatively short wave train. Then we can calculate for such particular wave train, we can calculate easily its spectrum. And spectrum, after calculation, is presented here by function sech. And now, if we take into account that in the process of propagation, within the framework of linear theory, each component of the wave spectrum decays independently, we obtain that at some distance x, the frequency decays according to this formula. So we have this factor which describes the frequency decay, the decay of the particular component of wave field. And because of such non-uniform decay of a frequency, we observe the apparent downshifting of the spectrum. So if initially spectrum was presented by this red line, when psi is 0, psi is normalized distance. But then, in the course of propagation, the amplitude of the maximum of the spectrum decays, and maximum of the spectrum shifts to the left. Here, blue line is multiplied by factor 6 to make it visible and comparable with the initial spectrum, and green line is multiplied by factor 30. So, as we can see, there is a frequency shift, but this frequency shift can be explained by non-uniform decay of frequency component on the left of the central part and on the right of the central part. So, according to this study, we obtained that when the product omega naught T is 14 for quasi-monochromatic wave train, we have that amplitude decays exponentially with distance, and we have decay of the maximum of the spectrum. But in addition to the maximum of the wave spectrum, we can define also so-called mean value, which is defined by this formula, and it represents actually a mass average, to a certain extent, mass average of the spectrum. And this quantity is presented here by blue line, and as we can see, for such defined spectrum, we observe a bit faster decay when omega naught T is 14, but when omega naught T is 4, we have quite notable difference between the shift of peak frequency and mean value of a frequency. So they are presented here. And also we have here the dependence of amplitude on distance. Within the framework of purely linear theory, we have such simple exponential decay. But in fact, if we take into account that we have to reconsider the equation when the frequency shifts. And so if we follow every time the maximum, the peak value of the spectrum, this means, for example, if we consider a green line, that at this frequency, the decay rate is different than in the frequency at 0. So if we take into account that the decay rate is different at each maximum value of the spectrum, we obtain that the decay is not purely exponential. At the initial stage, it is indeed exponential. There is no difference between blue line and pink line, but then we have such a difference within the linear theory. Now we can consider what happens if we take into account a finite amplitude of a wave. In this case, especially if we consider narrow band initial perturbation, then the wave field can be described by the nonlinear Schrödinger equation. Such approach was used by Alberella and Parao in their paper of 2022, and they augmented this equation by additional term here, which describes the dissipation of a wave field. Here the operator R hat in their paper was simply gamma omega cubed. So they considered the decay where where the decay rate proportional to omega cubed. And then they studied this equation numerically, and they, with random initial data, modulated by Gaussian envelope. So here you can see the results of their calculations, and you can see that if initially the waveform was presented by blue line, then in the course of propagation, we can see that wave spectrum decays, and there is a shift of the maximum of a wave spectrum. This figure, this panel, corresponds to relatively small dissipation coefficient. For bigger dissipation coefficient, the downshift of frequency is quite notable if we compare this yellow line with the red line in the initial instant. So the downshifting was also observed through the numerical calculations, but there are some critical points regarding these results. First of all, when we consider the nonlinear Schrödinger equation, we assume that the initial spectrum of the perturbation should be relatively narrow. But in this calculation, as you can see, the characteristic width of the spectrum was of the same order as the maximum, as the peak value of the spectrum. So actually, in such a case, this operator is unapplicable and should be replaced by another operator, which corresponds to the narrow spectrum. We did this work using the same equation, but we also took into account that coefficients of this equation depend on the frequency and on the ice parameter. I forgot to mention that in the study by Alberella and Parao, all coefficients alpha, beta, and CG were taken the same as for water wave uncovered by ice. In our case, we took into account ice cover, and in this case, the dispersion relation is presented here. This is a real part of dispersion relation as a function of k, where parameter m corresponds to the flow ice density divided by water density, and h is the thickness of the floor. This equation can be presented in terms of the dependence of wave number as a function of omega, which is given by this equation. And here we have, in this case, we have some critical value of a frequency. This critical value can be easily obtained from the denominator of this equation. And in this plot, we present real part by red line, real part of dispersion relation, and imaginary part multiplied by factor 50 to make it comparable with the real part. We also show conditionally the wave spectrum here, which should be relatively narrow with respect to the maximum value of the spectrum. All other parameters are shown here. They were taken from the paper by Albarella and Parao. But we also consider that the right-hand side of this equation should be considered as a function of omega in the vicinity of the peak value omega naught. By the way, the nonlinear Schrödinger equation was for sea water covered by ice in general were derived in our paper in physics of fluids, and all these coefficients are shown here for the particular case when we have broken ice. Then, as I mentioned, the right-hand side should be presented only in the vicinity of omega naught. This means that the decay rate, which is proportional in general to omega cubed, can be considered only around this frequency omega naught, some given frequency, and with small correction. Then, if we come back to the corresponding nonlinear Schrödinger equation, we obtain the equation augmented by this term. So we have such an operator, and then we can consider solutions of this equation, assuming that the right-hand side is relatively small when the decay rate is relatively small. So in this case, if we simply neglect the right-hand side, we obtain the classical nonlinear Schrödinger equation, which has such a solution. This is exact solution. In this solution, there are two independent parameters. One of them is amplitude, and another one can be considered as a correction to the frequency, sigma. Sigma is the parameter which plays a role of frequency shift, and we will see what is the dependence of the frequency shift and amplitude as functions of distance x. If we take into account small dissipation parameter mu, then we can obtain an approximate solution in the form of this envelope soliton, where all parameters now are functions of x. To obtain the dependence of these parameters on distance, we can use the balance equations. If actually the nonlinear Schrödinger equation has a number of balance equations. The simplest of them is when we multiply this equation by psi complex conjugate. In this case, we obtain this quantity n. And for quantity n, we have such a balance equation. Then there is another quantity p, which also depends on x. I will show you these two quantities n and p on the next slide. But before, as you can see, if mu is 0 on the right-hand side, we have that n and p are conserved quantities. This is very well-known fact for the nonlinear Schrödinger equation. But if parameter mu is non-zero, in this case, we obtain the balance equation. So quantity n is just an integral of modulus of psi squared. P is such a quantity and E is this one. Now, if we use a solution in the form of envelope soliton and substitute here in N, P, and G, then we obtain the set of two simultaneous equations for the amplitude and frequency shift. So we have two such equations. These equations are relatively simple, and they can be solved analytically. First of all, we can obtain a first integral of this set of equations if we simply divide first equation by the second, and then we obtain such a relationship between wave amplitude and frequency shift, where AC is some critical value which depends on the parameters of nonlinear Schrödinger equation and central peak of the spectrum. This dependence of amplitude on frequency shift omega is shown in this plot. So for typical and most realistic situation, when initial...
Sir, you are having 2 more minutes.
Okay. So in this case, we have such a most realistic dependence where A naught is the initial amplitude and AC is some critical value which was shown before. Then for the critical amplitude, we have such a dependence. And for supercritical value, we have this dependence, which formally predicts increase of amplitude, but actually the range of validity of this approach is restricted when this shift is relatively small in comparison with this limiting value. So analytical solution in this case can be presented for different values of initial amplitude. They are shown here. And after that, we can consider their dependence on X. I can show you in a minute, but before I have to say that this theory assumes that the frequency is constant. The central frequency is constant, but in fact, central frequency experiences shift. And as so, we have to modify the approach because all coefficients in this equation are functions of omega. And so if we modify our asymptotic approach and take into account that omega is a function of sigma, then we obtain such a nonlinear set of equations, which is not solvable analytically, but it can be easily solved numerically. And here you can see that the dependence of amplitude within the linear theory is exponential. Within the simple asymptotic theory, it is shown by this yellow line. And within the framework of this modified theory, we have such a red line. So initially, the decay rate of amplitude is 2 times greater than within the framework of linear theory. Here you can see also what happens with the frequency shift within the simple theory and within the modified asymptotic theory in comparison with the linear theory. Similar results were obtained by direct numerical solution of nonlinear Schrödinger equation. All these results are also summarized on these two graphics. One of them corresponds to the amplitude dependence on distance, and another one corresponds to the frequency dependence on the distance. In this case, we can observe that there is indeed a frequency shift. The scale here is from 0.92 to 1. So in such a scale, the frequency shift is quite notable. That's it, what I was going to present here. And I'm ready to answer your questions. Thank you.
Thank you very much. Is there any question?
Mike, do you have a question?
He is on mute. Yeah.
I do have a question, Yury. Yeah. I just wonder how much, you in the end, you need to parameterize the dissipation. It doesn't, It seems like how much influence does that have if you go back to the actual problem of the ice?
All right. So the idea is that if we consider, in any case, if we consider the nonlinear Schrödinger equation, we have to remember that this equation is applicable only for narrow band wave terrain. Okay, so this is by definition. When we derive this equation, we assume that wave amplitude is relatively small and dispersion parameter, this is dispersion parameter, is also relatively small. This means that width of the spectrum must be relatively small. Then, if we augment this equation by dissipative term, this should be in consistency with our assumption. So, in other words, this means that we cannot consider here function omega cubed, but we have to present this function omega cubed at least as a Taylor series and restrict ourselves by peak frequency omega naught and small correction, small deviation from omega naught. Only in this case, such equation is consistent. And within the framework of this equation, we can consider what happens with the initial wave train. Okay?
But I'm just sort of curious though, Yury, in the slide here, you've assumed this proportionality of the imaginary part, and then later on you kind of extract it, and it's like, it seems like you've assumed the answer here in a sense.
What do you mean?
Well, your predictions at the end about the attenuation sort of match with what you assume. You could change this assumption here. If you change it, you get a different answer, right?
Yeah. So, of course, we have to be careful, and we have to look what is the deviation of omega from omega naught. So this theoretical approach is correct only when this difference is formally relatively small. But
okay, I see that. Yeah.
Omega minus omega naught should be relatively small. But what is shown in this graphic, we can see that formally speaking, this maximum shifting can be -1/3. So this may be up to 30%, roughly speaking, 30% of omega naught. So actually, the realistic line should be like this one by blue line, not greater than 30%. So this deviation maximum is 30%. Okay, so we can predict. Yeah, one more interesting result of this study is that within the framework of linear theory, when we consider downshifting, we observe that within the linear theory, the spectrum becomes non-symmetric with respect to the peak value. But within the nonlinear Schrödinger equation, the pulse remains symmetric, and the spectrum also remains symmetric until adiabatic theory is valid. So there is a difference, and we can distinguish between these two mechanisms of decay, linear or nonlinear. Okay.
I am having a small question. Sir, that
Yep,
R omega proportional to omega Q, is it derived or is it considered from Alberolo and Parau paper?
actually, it is the result of averaging of these data. Okay, yeah. So as you can see, observations show that there are different exponent n from 1.9 to 3.6. We simply took some average value, n equals 3. But in fact, in the paper which we currently prepared for the publication, we considered the decay rate for arbitrary n. And then if we choose n equals 3, then we obtain the particular results which are presented here.
Okay, thank you. So thank you very much, sir. You can stop your screen sharing.